How about Liquor 3607 power grid maintenance? Give us a integer C represent C power station. That is the C number C nodes. They are from 1 to C. That is a one-based index. And also two-dimensional array connections. Connections that is the edge between those nodes. They are bidirectional. And also there is query array. The query has two types. For each query, it is has two elements. The first element is type. The second is in station number. So you say that maintenance check is request. If it is one, then it is check for station X. If X is online, then it resolves the check by itself. So it will return some number. If X is offline, then check result by the operational station with the smallest ID in same power grid as X. If no operational station exists in the grid, return -1. We know in the um, same operational station. That means um, in the same grid. That is they need to be connected, right? So we just need to find those in the same set which have the smallest number. So if we cannot find in this set online grid return -1, then station 2 does not return any numbers. It just gets station query 2 doesn't return a number, just get a station X offline. So the thing is that the query number does not necessary to be the same length of the return result because the query 2 does not return result, right? Let's look at the example. This query 1.3, right? Initially, all of the, it says that all of the station are online. So 1.3, that is option 1, and 3 is online. So we are going to return 3. And then query 2, we are going to turn, so this is the first result, it is 3, right? The query 2 are going to turn off option 1, right? So this will be off. So this query does not return any result. And then query 1.1, this 1.1 in the same in the same grid, you'll see the smallest online one is 2, right? So we'll get 2. And then we turn off 2, right? And then we query 2, the smallest online is 3, right? So the way we're thinking about this is that we should find those connections. For example, there are several connections, right? The sets which are connected, and we can use a connections array to find this one, right? And also for each connection, we need to find use a tree set to store those connection parts. And also, we can place this tree set in some kind of list of tree sets, right? Or tree sets array, a list of tree sets. And for every station, we should have a map which can have a key as a station, right? And the value will be the list of tree set, the index, right? So how can we create this map with index and also the list of tree sets? We can use the DFS, right? After we compose these two things, for every query, if it is 1, right? Then we just look at this map and find the tree set. And then we just get the first key from this tree set. That will be the result. And if the query is 2, right? what we need to do is that we also need to find from this tree set, but the thing is that we need um, to remove this station from this tree set so that all of the station living in the tree sets are online, right? Um, so to build this map and the tree set, there are two ways, right? You want to build the connection problem. One is the DFS, right? Another is unified. We are going to write both way, right? First, let's do DFS way. Okay. So we need a build a graph for DFS, right? Let's say graph equals new list. So because it is from C 1 to C, right? So let's say this is C plus 1. So we are going to arrays set O graph K goes to new array list. And then we're going to for array H in connections. We are going to have a graph for E0 add E1. Also, we are going to have graph E1 add E0, right? So this is an OC, this is an OE, OM, right? Whatever. M is a number of connections. And now we need using using DFS to compose two things. One is a map that is from every node. We need to find that we're going to have a list of tree sets, right? So this will be the index with the tree set. So we are going to have map because new hash map, right? So that is from station as a key, right? And we need to find a tree set's index. And also we need another one that is list of tree sets, right? Integer. And this one we are those kind of online components that we only place online one, right? Into into uh, uh, into this tree set. Initially, they are all online. So let's call I don't know what. Um, let's just call it list, right? So new array list. Those are online stations, right? Online tree set of stations. Then firstly is that we use DFS to compose these two data structure. So what we do is that for int I equals 1, I smaller equal to C, I plus plus, then if map doesn't contains key, right? We haven't visited this one, then we're going to have a index that is a index of list of, in a list, right? Will be list dot size. Then we are going to have we need to create a new tree set integer. So tree set equals new tree set. Okay. And we're going to have this tree set add this kind of um, we're going to have a list, right? List add this tree set. Then we're going to have DFS graph, and current node station is I, and our ID, and we should have a map, right? And also we need to have a list. So this will be the first part. Let's write DFS first. That will be an easy one, right? Private void DFS. So we're going to have a list of integer, this one as graph, and also into parent, into index, map, integer as map, right? And also list of tree set integer. This one as list. Okay. So what we do is that we need to add to the map, right? Map put current and index. Also, we need list get index. We're going to add current. Right? So what we do is for int next in graph current. Then we are going to have so we just need to check whether it already contains, right? So if map doesn't contains the of next, then we're going to have a DFS graph next with company ID and map and list. So this will be the DFS part. After we use the DFS, we compose this map in the list. So for our query, right, we need a online Boolean array. Let's use offline. Okay, offline equals new all of that currently they are set as a false, right? New Boolean C +1. Then what we do is set a list of integer result equals new array list. And for every query in queries, so we know this ID equals map get query one, right? And tree set integer will be let's say set equals this list get ID. So if this query is type 1, right? Then let's say if this is not offline, if not offline query 1, then our result are going to add query 1, right? Else we need to find its this set, right? So result add so this set, if this is empty already, right? So if it's empty, we're going to add -1. Otherwise, we're going to have this set, this tree set first. So this is query equals 1, else that is query equals 2. We're going to have if this is not offline, right? Offline Q1. We just set this one as offline. Offline Q1 equals true. And also we are set remove Q1, right? So in the end, we return this. This is a list. We also need to change this to an array, right? Return result string. Um, we are mapped to int integer. We are going to have int value, right? And to array. So this will be the code. Is add tree set. Okay, let's analysis the complexity, right? So to compose this graph, right? Compose this graph, this is an OC, right? This is OC. And this will be all edge numbers, right? So let's say M connections, this is all M, right? And here, um, we are we are doing the DFS, right? So there are C loops. And for each DFS, we are going to have add to the tree set. So this one will be C log C operation, right? Um, and for the query, right? Query that is Q loop and that is also tree set, right? So that will be Q O Q log C, right? So this will be the time complexity will be C plus M plus C log C plus Q log C. Space will see this is C, right? And also this kind of connections, how many connections? This is actually OM, right? And this is a connection. This is also OC, right? And um, in the tree set map, this is also OC, and the list is OC space C, and there is the query. So we'll say space is just a linear, right? But for time complexity, we should add those operations OC, OM, C log C, Q log C, right? Um, for Python, use this DFS because the Python stack is not that many. It may be OOM. We can change that to be using a stack to replace the DFS way, right? To do the iteration way. Because for this DFS, actually, it is do not have any branches. For every node, it just have one child, right? So actually, we do not need to write DFS. Or we can another option is that we can write a union find way for this, right? So union find, let's also write the union find code. So we're going to, the union find is that we use these connections to put those kind of sets into different subsets, right? Different connected components, and we use a map. So then we create a map, right? We also need to create a map and a tree set, and then we just find the parents. And for all of the connections which belong to these parents, we're going to put it into this map. Um, and we have also need same thing. We need to have a node uh, to put the parents uh, uh, map. Still, let's put a node to not the parents. Let's have a node to tree set index, right? Otherwise, our parents we tree sets will not use a list of tree sets. We can still use a parent map. We need two map, but let's be consistent. Let's still have a map to index, right? So then it will be the same as TFS way, right? So we just write quick code quickly. So class union find, and we're going to have int father. So what we do is that the public union find int and we're going to have father equals new int. And so what we do initially for int I equals 0, I smaller than I plus plus, we're going to have father I equals I, right? And public void union int A int B. So let's say int FA underscore A equals find A int FA underscore B equals find B. So if FA underscore A doesn't equal to FA underscore B, then we set further FA underscore A equals FA underscore B, right? So also we need int find int x. So let's say if x already equals father x, just return x. Then we're going to have father x equals find father x. So this is recursively to compress the path return father x, right? So this will be unified find class. Then we for our class we need to compose. Let's create a unified help class first. UF equals new union find the C platform, right? And we need to connect for each edge connections. We're going to have UF union E0 and E1, right? Um, then do we need a map to index? Actually, we don't need a map to index, right? We just need a moment ago when we submit our solutions, right? We don't need a actually I don't need to create two data structure, right? we just need to create a one map index to tree set is enough, right? Here, we can simplify it. Um, yeah, can write this with a bit concise. Okay, so um, so let's we just need to have map index to tree set. That's enough, right? For DFS, we the same thing. We just need a map station to tree set. So we don't need two data structure. So I'm going to improve that a little bit a bit later, right? So we're going to have map equals new hash map. Then for int I equals 1, I smaller equal to C, I plus plus, we're going to have map impute if absent UF. Let's have the key to be UF find C, right? And so this one K goes to new DFS. Let me think. DFS, the things that DFS we need let me take back my thinking. DFS the things that um we need a two data structure because there is no such concept of parents, right? So those kind of we still need to use C to find the tree sets index, right? Um, so for DFS we use two data structure. But here, because we have parents, right? Because union find, we can find the uh the top parents. So this will be unique, right? So we just need to use one data structure. Tree set, and we're going to add I. So then we're going to have list integer result equals new array list, and we need a boolean offline equals new boolean on C plus one, right? Then what do we do is that for every int query inquiries, we are going to have int ID equals UF find query one, right? And so we're going to have tree set integer set equals get index. So if query 0 is 1, right? If this is 1, we're going to have if this is offline. So this is the same code as what we do a Mongo 1. Then we're going to have result. We're going to add query 1. If it's not offline, then add it. If it is offline, we are going to result add is set is empty, right? If this is empty, then we add -1. Otherwise, we set first because this tree set. So if else that query is 2. So if it's not offline, if not offline Q1, then we need to set this one as offline Q1 equals true. And also we need to set, remove this Q1, right? So in the end, we need to convert this result to a list return list result dot string map to integer dot int value the value to array. Because this is no if find the Q1 index cannot invoke because this variable you say that so you say that this is not right. Map. So the things that this is a find you have find a Q1 get ID if remove Q1. Well, not offline. Set this as offline. Then remove Q1. Why there is a non-pointer? C find a new tree set. Add I. This is correct. Result Boolean should be C plus 1 for every query. We're going to, if Q0 equals 1 offline and offline, this it's not offline, then we add this query and it's empty. Else, if offline Q1 set is it looks like a set is empty. Let's set this as parent. Right? Parent will be much make sense. Parent, but still, why there is C plus 1 each connection we connect then we compose the tree map, the hash map. So this tree set into this result Boolean. Where every inquiry's parent equals find this query tree set equals get parent. If type is 1 and it's not offline, we add it. else if it's not offline, we set this one as offline. So why set is empty? Cannot remove. When we remove, we remove which one has problem? Two. We didn't remove twice. So what's the problem? Map compute if absence data result apply C++ inquiries. If this one equals 1 and compute, I didn't see any problem here. So connections, queries, let's execute. So this one doesn't have any connections, right? Doesn't have any connections. Then then we this one will have problem, right? Because we don't have any connections. We don't have any connections. UF find C. We don't find we don't have any connections. Then find us. This is I, right? Sorry. Otherwise, the key is always unique. So this is a small typo. Doing the union find, let's also analysis the time and space complexity, right? So this will be there are this will compose union find. This will space OC, right? But this one is OM, right? Or OH, right? Whatever, OM and for this tree map, we every time we find this is O, we can consider find like a constant. For find, we add this is every log operation, right? Because that is tree set. So for every node, we add it to tree set. So C log C, right? And here for the query, right? Query we also query we need from the tree map. So this is also an OQ log C, right? For the space here that is OC, right? OC, and also this is OC, and this also OC. Well, C space is linear, right? We can also write a Python code for this. Class union find. We're going to have def on the store init self and which has the integer. We're going to have self dot father equals list of range n, and we're going to have a diff find. This is also self x int, right? So this we need to return int. So what it is if self dot father x doesn't equal to x, then we're going to have self dot father x equals self dot find self dot father x, right? So this is a path compression, and then just return self dot father x, and also we need to define union self a int b int. So this one, so FA, FB equals to find A and find B, right? So if FA unequal to FB, then we'll have self dot father FA equals FB. In our main function, that's first, we need to create a union find C++, right? Then for UV in connections, we need to have UF dot union U and V. Then what we do is that we need to have map, right? So this map is parent to tree sets, parent to tree to sorted set, right? Sorted set. Whatever. Into that, okay? Because so for I in range 1 to C+1, right? So we're going to find a parent because you have got to find C to find I, right? Remember just a Java code we use C, right? There is a problem. So if parent not in P2 set, we're going to have a P2 set parent equals sorted set. Okay. And then we're going to have P2 set add. Okay. So doing like this, we create a map. So then what we do is for type and X in forest. So we'll say index equals or parent equals UF dot let's don't use same. Let's use PR equals UF dot find X, right? Parent. Then we'll say this sorted set equals P2 set parent, right? So if type equals 1, we're going to so type T, right, equals 1. we're going to have if not offline x, we're going to have result append x. Else, we need to result append SS set 0 if it's not null, right? If SS set else, that is which append manifold. Else, that is t equals 2. Then we're going to have if not offline x, we're going to have offline x equals 2. And also we're going to set discard x. And in the end, just return result. Find is not defined. Self-defined, right? Should be. If FA, this is FP, right? P2 set, and we should have P added, right? Offline is not defined. We should, let's, oh, we should define the offline, right? So, offline, and also we need a result. Offline equals false multiplied by c plus 1, and also result, let's say this is okay, so this will be the code.